Hi, my name is Anna Rensch and I'm a PhD candidate at the University of Guelph. Today, I would like to talk about spatial cognition of laying hen pullets reared in housing systems with varying complexity. Laying hen housing is undergoing a major shift by turning away from barren conventional cages towards more complex alternative housing systems, like furnished cages or the aviary depicted here on the slide. While the EU has already made that change, Canada is preparing to alter all laying hen housing to alternative systems by 2036, and the US is experiencing a market-driven housing conversion with legislation varying between states. Aviaries are multi-tier systems with resources being distributed throughout the vertical space. Their benefit is that they offer space to perform a large range of behaviors such as perching and dust bathing. On the other hand, they require the cognitive ability to navigate complex, three-dimensional structures. The high spatial complexity can lead to birds with injuries resulting from unsuccessful aerial transitions or emaciated birds that were unable to locate food or water. Both are serious welfare concerns in the commercial egg production. In order to get hens with the appropriate spatial navigation skills, hens need to be raised with appropriate spatial stimulation. From literature, we know that chicks need to learn specific spatial skills within the first few weeks of life in order to successfully navigate three-dimensional structures as adults. For example, rearing without perches negatively impacts spatial navigation, and increased complexity during rearing increases space use and spatial cognition. In recent years, the importance of the rearing environment has been stressed more and more. It is generally accepted that a closer match between rearing and adult environment is better, meaning that hens living in an aviary should also have been reared in an aviary. Chicks are moved into their pullet housing right after hatch, where they will stay for approximately 17 weeks before being transferred to their adult housing. In pullet aviaries, chicks are confined within brooding compartments during the first few weeks for manageability and their own safety. When the brooding phase ends, the systems are opened up, giving pullets free run of a litter area and multiple tiers. The design of pullet aviaries is very variable, with little to no guidelines. Generally speaking, rearing aviary designs can be grouped into three distinct styles. In the three different styles, the brooding compartments especially differ significantly in their space and complexity. We were asking how the environmental complexity, especially during the first few weeks of life, and pullet genetic strain affects spatial cognition of pullets. Our hypothesis is that the environmental complexity during the brooding phase dictates space use opportunities, which in turn affects development of spatial cognition in laying hen pullets. We predicted that a more complex rearing environment during the first few weeks of life results in pullets with improved spatial cognition. We also expected to see strain differences, and maybe even different responses to the different rearing styles between different genetic strains. To answer our question, we raised two flocks of laying hen pullets in each of the three distinct styles of commercial pullet aviaries, as well as conventional pullet cages. We raised two commercial strains of laying hen pullets, the white-feathered Lohmann-selected Leghorn Light and the brown-feathered Lohmann Brown Light. Here you see a side view of an aviary, a picture of the brooding compartment after chick placing, and a photo of the free-run phase. Aviary Style 1 offers the least spatial complexity, where during the brooding phase, chicks are confined in cages with two perches. Once open, the free-run phase offers access to a litter area and three system tiers. Aviary Style 2 offers a bit more complexity, with an elevated platform and three perches in the brooding compartments. The free-run phase offers a litter area and two system tiers. Aviary Style 3 has an open concept brooding compartment, where chicks can access the whole length of the barn, a swinging platform and 6 perches. Again, the free-run phase adds a litter area and multiple tiers. This aviary is the most spacious and complex of the three. Bird density was kept consistent between all three aviaries in terms of litter and floor space per bird. Conventional pullet cages offer minimal complexity, with nothing but a drinker line inside a cage. There are no elevated perching structures. As you can see on the right-hand side picture, things get pretty tight towards the end of the rearing phase. Bird density in this system was according to the Canadian Code of Practice. At 12 weeks of age, pullets from all 8 treatment group combinations were moved into 8 pens, where they were gradually habituated to the teammates arena, first in groups and then individually. On the 5th day of habituation, each individual was assigned a reward site and associated color cue, and was forced to experience both arms in a short training phase. Reward site and color cue were balanced evenly between all individuals. During their 14th week of age, pullets received a set of trials in the teammates. The goal of the test was to determine how many trials a pullet needed to learn where her assigned reward site is located. Testing ended when a pullet either succeeded in 4 out of 5 consecutive trials, which was our predetermined learning criteria, or after a maximum of 15 trials. This video is from the training at the last day of habituation, where the pullets were encouraged to explore the rewarded side. The rewards included food in form of sweet corn and mealworms, as well as an escape option for pullets that were not food motivated. During the testing phase, each trial lasted 90 seconds unless the reward was reached before the allotted time ran out. Whenever a pullet walked into the unrewarded arm, the rewarded arm was closed off as a consequence, and she would have to wait out the remainder of the 90 seconds in the maze. We used 2 flocks of pullets, with 4 rearing treatments each, as well as 2 strains in all treatments. 272 pullets were tested in the teammates. 251 reached the learning criteria within the 15 trials, though all pullets are included in the analysis, which consisted of a survival analysis done in R using a Cox proportional hazard model. In this model, a hazard is defined as a pullet's risk of reaching the learning criteria within a certain time frame compared to another pullet's risk during the same time frame. The data was right-censored, as not all pullets succeeded in reaching criteria within the observed time. The fixed effects were rearing style and strain, as well as their interaction. This table presents the minimal, maximum, and mean number of trials needed for every group, as well as the sample size and the percentage of pullets that reached learning criteria. I would like to quickly point out some interesting numbers. If you're looking at the maximum number of trials needed, you can see that white pullets in aviary style 3 and 2 were the only ones where not only everyone reached the criteria, but also everyone learned within less than 15 trials. On the other hand, conventional cage pullets were the only ones were the ones with the lowest number of pullets reaching criteria. Both rearing style and strain affected learning speed with no interaction effects. Here you can see the proportion of birds reaching the learning criteria on the y-axis and the number of trials on the x-axis. The dotted lines indicate the time point where 50% had reached criteria. White pullets are in blue and brown pullets in red. Whites learn faster than browns, with the hazard ratio being 1.87, meaning that a white pullet would be at a 1.87 times higher risk of reaching the learning criteria compared to a brown pullet within the same time interval. On this graph, you can see style 1 pullets in red, style 2 in green, style 3 in blue, and conventional birds in purple. There was no difference between the different aviary reared birds, as you can see by the overlapping confidence intervals. Though you can see that there is a grouping of green and blue and one of red and purple. And indeed, pullets from aviary style 3 learn faster than conventionally reared pullets, as did pullets from aviary style 2. Checking our predictions. Rearing complexity did improve spatial cognition, and we see a clear strain effect. The strains were not affected in a different way though. From this, we can conclude that white pullets are better suited to learn the location of new resources, which would mean that they should have an easier time adapting to the new aviary after transitioning from pullet to adult housing system. We see that pullets reared in aviaries with complex brooding compartments develop better spatial cognition compared to pullets reared in conventional cages, which is neither surprising nor new. What's interesting, however, is that pullets reared in aviaries with more simple brooding compartments do not show that improvement. This suggests that when choosing a rearing aviary, the spatial complexity should be taken into consideration. This dataset will be put into context of tests assessing physical navigation skills, as well as space use assessments in the different rearing aviaries. Furthermore, brown hens from aviary style 1 and 3 were further observed in an adult aviary, where we assessed their space use and production. And with this, I would like to thank our funding agencies as well as the staff at the Arkel Research Station for making this project possible. I would also like to thank my supervisor Tina Wadowski and all students and research assistants that helped me collect the data. I appreciate everyone who listened to this talk today, and I happily answer any questions that you might have.